talk about is a model for statistical for tensor PCA, and I thought this is an interesting topic since there are tensor experts in the audience, and this joint work with Miller and Sharp. So what I'm going to say is it's fairly simple. Okay, so let's start. The model is like this. You have data set that you represent as a tensor of order k and dimension n. So this is the two notations that you have to remember. So what does this mean? It means that x is just a table of numbers, xi1, ik, with indices i1, ik in the set of first n integers. Okay? And so this is my data. And for most of the examples, I will take k equal 3 and 4, okay, and of course 2 for comparison. And okay, so my model will be the following: that x is equal to a number beta. This is you can think of it as the signal to noise ratio times v tensor k, v0 tensor k. So this is the outer product k times of a tensor with 0 plus noise. Okay, so this is the signal. This is the noise. And beta is the signal to noise ratio, and v0 is again a vector. Right? Okay, and I'll be talking about the case in which z is random, so it has high independent components, Gaussian component. Okay. And okay, now we have to choose the normalization for the entries. I like the following normalization: zi 1 to k normal 0 1 over n k minus 1 factorial. For some reason, this is nice for doing calculation. The 1 over n is the right scaling, so that things happen when beta is of order 1. Okay, and okay, z is rotation invariant. Meaning, if you rotate the coordinates, remains unchanged in distribution.
So there are n to the k independent random variables.
There are not n to the k. Good point. So it's Gaussian symmetric. What the symmetric means? It means that z1, 2, 3, 4 is equal to z2, 3, 1, 4. So there are basically n to the k choose k. Where k factorial independent, a bit less because there is the diagonal, blah, blah, blah. So is everybody okay with the model? Right? So this finishes the part a statistical model for tensor PCA. So my problem is, given x, estimate 0. I will not really justify why I'm interested in this problem. This kind of model has been studied in the case of matrices a lot in statistics, under the name of sometimes, generally the spiked model. So this is statistics, typically in the case k equal 2, and typically one is interested in rectangular matrices rather than in symmetric matrices, but here we'll keep to rectangular. And I don't know who is the first one, but perhaps Ian Johnston. Early 2000, studying this kind of models in statistics. Okay, and okay, so I want to estimate.
The signal is also symmetric.
Yeah. So what this means is that is the tensor of order k whose entry I, j, k, l is v0i, v0j, v0k, v0l. Okay, so this is clear.
Is V0 a unit vector?
Yeah. Okay. Good question. Good point. So v0 is a unit vector. Otherwise, we come to
and the scaling, if I understand the scaling here. So V0 is a unit vector, beta is just some scalar, right? Z is
Order.
Gaussian and n to the k, and
it has n to the k entries, and each entry is of order 1 over square root of n.
right.
Forget about
k minus 1 factorial.
Yeah, forget this k minus 1 factorial. So if you want, I'm going to keep, most of the time I'm going to be interested in 3 and 4. So this is a constant scaling, right?
Oh, sorry, I see. Yeah,
I'll chase constants in some of the results, but not in all of them.
Right.
Beta is a parameter, right? Which you have not specified yet.
Beta, so what? So the question is, okay, give estimate with 0. So you might think that this is going to be easy when beta is humongous, and hard when beta is very small. And I want to understand when it's easy and when it's hard.
Is the symmetric model of noise crucial? Like if you just show
No, I think okay, some of the results we did it actually. It's a little bit more difficult than the completely independent model. It's actually a little bit, we shoot at ourselves in the foot by looking at this symmetric model, but okay.
Right, and you're thinking about getting 1x, and you're trying to estimate.
Sure. So I get one big tensor. I want to estimate this big. Fine. So okay. I want to do estimation. So what is my loss? My loss. Okay. Say loss. D hat is 1 minus. Okay. You cannot always estimate the sign of it 0. So at least for k even the sign is not known. So let's say up to a sign. Huh? It's scalar product. This is my estimate. So let me just recall what happens in the case k equal 2, because this is a little bit of context, and this is very well studied in statistics and probability theory. Probability theory has the name of low-rank deformation of a Wigner matrix, and okay, I cannot go there. 2. So what happens there? There is a phase transition that is is attributed to Belarus, Péchet, and others, Paul, and there are hundreds of papers on that. Capitaine, Ferral, Knowles, Yin, any, but depending on the signal to noise ratio, I'm going to plot you the distribution of eigenvalue of such a big matrix. For beta less than 1, you will see just the Wigner semicircle between 2 and minus 2. And it's basically, okay. So these are distribution, eigenvalue, empirical spectral distribution. You don't see any spectral signature of this rank 1 thing. And in fact, it's impossible, let's say impossible, to estimate V0 better than random. I can give more qualification on that, but take my word for the moment. For beta bigger than 1, you see something like that. You see the Wigner semicircle, but then we see an eigenvalue popping out, and it pops out at beta plus 1 over beta, and if you take this eigenvector, this has a loss strictly less than 1. So here the loss equal 1. Here loss is less than 1 minus epsilon, and goes to 0 with beta.
Okay. Very quickly, with your normalization, I mean, the Wigner top eigenvalue, will it be exactly 1 for the random? Is that the normalization is achievable?
Okay, so good point. Good point.
See if you have an extra.
2, yeah, so it's the top is exactly 2. This is, with this normalization, the entries for the case 2 are 1 over, variance 1 over n, so the top eigenvalue is 2.
I see.
This is the standard normalization. And the other is at beta plus 1 over beta. So there is a phase transition at beta equal 1. So the picture in this case k equal 2 is the following: as beta increasing, somehow here it's 1, here it's easy. It says that it's possible and can be done by just by eigenvalue decomposition, and here it's just impossible. Right? So there is really no statistical method that gives you the answer. Okay, so what happens for k k bigger. So why the scale 1, beta of order 1 is correct? Because in this case, what it makes sense to look, the first calculation to look is the operator norm of the noise, the largest singular value of the noise. And you can compute it is exactly 2, but the important point is that is of order 1. So this is Furedi, Komlos, Gaiman, many others. Okay, so let's try to think about k bigger or equal than 3. What is the operator norm? What is the right generalization of operator norm? So I claim that the right generalization is also appears in the literature. Is this object is the max over v in the n-dimensional sphere of z tensor product vk. Okay. So here, what this is really is, this is really sum over I1 ik z I1 ik bi1 bik. Okay. If you have tensors, there is a natural scalar product. So you take the scalar product, take this tensor versus the outer product of b with itself k times. In coordinate, it's just simply like this. And so the first question to ask is, what is this for a random noise object? So let me call it this HZV. So some of you know that I'm a physicist at heart. So this cost function was studied by physicists since the 90s under the name of the p-spin model.
So one clarification. So do we just have one sample of
Yeah.
this?
Yeah, you have just one tensor.
Okay.
So n to the k numbers. Okay, p-spin model because a p is what physicists call k. Okay. And so Crisanti, Sommers did physics calculation, and then there are rigorous results by. There is a very nice paper by Benarus. Okay. The order is Haufinger. Benarus Czerny. This is late 2011 perhaps. Okay. So, and then there is a paper by Talagram that is hard to decode. Okay. So the basic results of this is the following. Well, let me see. It's the following, that if you look at limit n to infinity z op, okay, so you take larger and larger metrics. We know in the case k equal 2, this is classical random metrics theory. In the tensor case, this is, okay, so far I can see it's not yet settled mathematically. It's settled for k is even. And this has a limit and is some number mu k that has a messy formula. And for k general, this is at most the same formula for k odd. So this is k even, k odd. So I will not write the messy formula, but just to convince you that these things are very well, and this is just very sophisticated math. I'll write you, numbers. Mu3 is 2.870, and mu4 is 3.588. So, this is the right normalization. If you don't care about precise number, the operator norm in this sense is of order 1.
So this is only the symmetric case, or also the
This is the symmetric case. I think the non-symmetric case, I think it's quite more difficult. I don't think there is. I'm pretty sure there is no result on that.
And what is the statistical model? What is the thing?
This is just Z is the same as I'm saying here. It's Gaussian.
But what is the physics?
The physics was invented in the 90s by physicists as really a toy model for how glasses behave. Okay, so let me make a remark here. That is related to this question. Okay, for perhaps one simple remark. Remark one: You can do simple stuff on this Z if you are not interested in these very cool numbers. For instance, you can do Sudakov-Fernik, and Sudakov-Fernik will give you that this is less than k. You compare with this is a Gaussian process on, this function is a Gaussian process on the unit sphere. You compare with another Gaussian process that is easy, and you get this. Okay, so this is quite a bit more than this Sudakov-Fernik. This is of order square root of k. Second remark, okay, you can do standard Gaussian isoperimetry, and you get the disconcentrates. Okay, so these are fairly fair, so concentrates are on the order square root of n. Third thing, okay, so related to Anima's question, okay, this paper actually is about much more than this, and it's about showing something fairly amazing. Fairly amazing thing is following. If you look at HZD, this is a function on the unit sphere. It's a smooth function. It's a polynomial. This has exponentially many local maxima. Okay? So in the case k equal 2, there is only one local maximum that is the principal eigenvector. In this case, there is exponentially many. Further, they are not all the same value. They have values between. What? It's the Rayleigh quotient. Okay, so they have the local maximum have values between mu k, that is the global maximum, and some other eta k. So if you just look for a local maximum, you miss this value. So this is it. Well, they know everything. They know also the number of these local maxima. I mean, the expected number. Okay, so eta k, for instance, one fun thing is to run gradient descent and check whether you hit eta k. In fact, you do it. This is homework. This was a bit of a detour.
When you say exponentially, exponentially in what?
Exponentially in n. Okay, so this tells you, so the maximum likelihood estimator is just maximizing that cost function. This tells you that probably when beta is less than the operator norm, this has no hope of working, and in fact we have a theorem. It's not hard. Theorem that, okay, if beta is bigger than mu k, then loss is less than, okay, some constant. Actually, the constant is 1.1 times mu k beta. And if beta is less than what? Square root of k over 10. Okay. So this is loss of maximum likelihood. This is loss of any estimator is bigger than, okay, some constant, 1 over 32. Okay. So this is just analyzing whatever that cost function and simply some simple perturbation bound. This is some simple information theory argument. Well, these are off by a factor, and this is of order roughly square root of k. This is square root of k log k. This is a bit smaller, but roughly the picture that emerges from this is, that if this is beta, this is roughly mu k, so square root of k. Here it's impossible, and here is possible to estimate V0. Okay, so the important thing here is that I want to emphasize is that we chose beta correctly, so this happens to be the scaling correctly, so this happens to be theta of 1 with respect to n. So once you see this, you ask yourself, okay, can I do it in polynomial time? Okay? Can I do it in polynomial time, and probably the first idea that comes to your mind is power iteration. Okay, so this was studied by a number of authors in the past and in the present, including Sharp and Nima, etc. Here the model is a little bit different, but the ideas are quite similar. So this means you take, if you have a vector v, I do x curly bracket with v, means that I do contraction over k minus 1 of the indices. So this is the tensor, the vector that index k has xi1, g1, gk minus 1, vg1, vgk minus 1. Okay, and what I'll do it is I'll just iterate the following: vt plus 1 equal x vt over x vt. And I initialize that v0 equal y for some y of norm 1. Why I want to initialize to some non-trivial point? Because if I initialize to 0, this is not even well defined.
It's not a great idea to use V0 for that.
What?
You used V0 already for
V0 was
Anyway.
rank 1.
Yeah. This is my bad habit. I put iteration with upper index. I realized that.
And you're going to analyze with many restarts of the power iteration?
Not exponential restarts. That would work.
No.
What's that?
It's not clear, even with double, but
Exponential? I suspect there's some ball that's able to. It's got to be a local minimum.
Okay, so let me say what is the problem with this algorithm. So x is again signal plus noise. So let's do the naive calculation that actually is very instructive of assuming that basically this random matrix is independent of this vector v. This is false, the calculation is incorrect, but the result is correct. What you get is v0 vt k minus 1 v0 plus g. Now the beauty of my normalization is that this g now is normal 0 identity over n. Okay, perhaps. I'll show you 0 identity. And then, so this means that v0 vt plus 1 is basically beta, take scalar product of this v0 vt k minus 1 plus small error. Okay, and you see, if you want this to be bigger than this, you need somehow x beta x to the k minus 1 bigger than x, so x bigger than 1 over beta x to the k minus 2. Okay, so this is the value, how much progress I'm making at iteration t. And the progress at the next iteration is this. To make any progress, you want this. And in fact, we have a theorem. Okay, so this is again, this is very simple again. Some triangular inequality.
X is not the tensor. X was the tensor, right? So now this.
No, okay, so let's see.
That's,
Okay, let's make all it v0 vt. What I'm saying is that in order for the scalar product projection along v0 of my estimate to improve, I need this to be bigger than this. That means that I need to be in good shape to start with. Okay, so the theorem says, okay, if t is bigger than some constant of beta k, then if my initialization y v0 a scalar product that is, okay, I'll omit constants here, Z operator norm divided beta, and then this is 1 over k minus 2. Then loss less than Z. Okay. So you need a pretty good, so loss after t iteration. You need a pretty good initialization. So let me make a few remarks. Also here, so first remark is again this is very similar to again a result by Anim, Sham, etc. Now if you take random initialization, then this is of order 1 over square root of n. And if I assume this is of order 1, which is in our case theta of 1, this requires beta bigger than, oh, okay, so here this is wishful thinking. So this is what this argument gives. Gives that this should be bigger than 1 over beta to the k minus 2. If you do the proof, you lose one guy here because you do a wrong triangular inequality. If you do the naive proof. Okay. So for my story, this is okay, but it would be interesting, interesting to improve this exponent to 1 over k minus 2. Anyway, for random initialization, this guarantees that the algorithm converges, beta is bigger than n k minus 1 over 2. And so this is what the theory says, that the heuristics, that should be the correct thing, say something similar. Okay. So the heuristics say this, the theorem says this. I think this is the correct result. Okay, and two similar results we can obtain. Similar results can be obtained with what we call approximate message passing algorithms. That is a sort of glorified power iteration in which we can do some more tighter analysis in the limit, so we can get all sorts of constants. Eraser. So let me summarize now the picture. So this argument here is heuristic because it has, I'm assuming here that this is independent of this, which is incorrect. And this argument gives the condition this. And I believe that this is the condition that is tight. If you do the analysis with the triangular inequalities, you get this, which is not tight by factor square root of n.
But the lower bound is just a constant, right?
Yeah, so this is the interesting, the cool thing. Excellent point. Now the picture is the following. There is theta 1 here. Here it's just impossible statistically. Here it is possible, but we don't know how. And then there is here, okay, let me write here the heuristic threshold that doesn't change much the story. So for k equal 3, for instance, here there is, for k equal 4, this is 1, and this is just power iteration. Okay. So here we can do it very easily in a constant number iteration. Here we can do it, but we don't know yet how. And here it's just impossible.
So there's a sort of different power method that you can do. You see here you're fixing k minus 1 of your arguments and choosing the last one to be the best. Instead, you could fix 1 and apply a k minus 1 algorithm recursively each step. It costs you more time, but presumably it gets you...
So what do you mean?
The algorithm is you count the current...
So you change one of the vector at time.
You fix only one vector. No, you are changing only one vector, right? You're finding vt plus 1. I'm going to find vt plus 1 as follows. I'm going to fix one of the v's to be vt, operating on the tensor, then I get a k minus 1 tensor. The k tensor operates on one vector, gets me a k minus 1 tensor. I go and run recursively a k minus 1 optimization algorithm. Recursive.
It's a black box. Okay.
Recursive.
Okay, I think that this is related to the next thing that I'm going to talk about, but it's not
Presumably
exactly.
it gets you better data, for smaller data it can get you an answer, presumably.
Yeah, I think so. I think so. And again, this I think it's.
It takes more time because you have to do recursive
Okay.
also, yeah.
Okay, so there is another idea. So this is an excellent idea, but there is another idea that I think it's related. Is unfolding. This also appears in the literature. So what is the idea here? X is a tensor of order k. So this corresponds basically to n to the k numbers. Right, so I make a matrix out of it. Okay, and okay, so just by counting the stuff that you have, this matrix must be of dimension q times k. N to the q times n to the k minus q. Okay, now the idea is that if you look at this matrix is what? Is beta and then b0 power q seen as a vector and b0 tensor k minus q seen as a vector transpose plus the unfolding of the noise. Okay, and then the algorithm is just you do the principal component analysis of this M. Do PC of M. So this is, I think, related to what you're saying because you can choose Q equal 1. So this is basically as applying, a very skinny thing to 1. If you think of computing PCA by doing power iteration now in terms of matrices, this is, I think, related to what you're saying.
This won't give you an outer product of KQ things. I mean, it won't necessarily give you a rank 1.
Right.
Solution in
Sure,
this, yeah.
sure, of course. Finding rank 1 solutions is not very easy. Okay, so now this will work depending on, the way it works, it depends on the norm of this noise operator now. So we have, a simple theorem that says the following, that if you look at the norm of operator norm, now this is a matrix, so it's standard operator norm. So what is the heuristics? The heuristics is that this should be the size of the entries, that is of order 1 over square root of n, plus what you would obtain by a Wishart matrix with the same dimensions, right? So a matrix with IID entries. This matrix doesn't have IID entries, of course, but you might hope that, because of symmetry, but you might hope that the same work. So this means n to the q over 2 plus n to the k minus q. In fact, this is true up to constants. This heuristic is true up to constants. Okay, so what does this imply? This implies that this works. Okay, let me write a bit more precisely. If beta is bigger than this object, than this norm, so this is n to the max of q minus 1 over 2 and k minus q minus 1 over 2, then the loss. Okay, let's say it goes to 0. Okay, I can write in bounds, but doesn't really matter. Okay, so remarks. First, this suggests that you should choose q so that these two exponents are as close as possible. So choose, square it have as square as possible. So this appears also, these heuristics, in a different problem by Goldfarb, I think, and others. Second, okay, also here the boundary realities is loose in the sense that heuristics, okay, let's say if it is as square as possible, this means that it's sufficient to take beta larger than n to the 1/2 and then CL of k over 2 minus 1. Okay, so basically k over 4 in the exponent. Heuristics suggests that beta bigger than n to the k minus 2 over 4 is okay. So this is not exactly the same, and in some cases we can prove it. So can prove for asymmetric noise. Okay. So what does this tell us about our picture? Now the picture, perhaps I'll do it here. Okay, again for k equal 4. Okay. So if we evaluated this for k equal 4, you get that n here is power iteration. Here unfolding works. And here is square root of n. Okay? And you can repeat the same picture, perhaps again to your point. You can compute, again, here I'm plotting the exponent that I conjecture to be correct, but you see, the difference is big because this goes like k over 4, and this goes like k over 2. Right? So if you do repeat the same for k equal 3, you get power iteration, here square root of n, here n to the 1/4, here unfolding. Here it's possible, but we don't know how. There is theta of 1, and here it's impossible. Okay, now I'll try to okay, so how do you say? I want to show a few figures of simulations for this case. Here are fantastic.
Quick question. Why do you say it's possible, but we don't know how? We have
Maximum, we can prove that maximum likelihood works. But, it's NPR to solve the maximum likelihood problem, and I don't know of any algorithm that does it even under some statistical model. So I cannot prove that it's hard in this regime, but I cannot prove whether that it's polynomial.
And this unfolding method, so you'll not get a rank 1 component, but you'll again iteratively do a rank 1.
Okay, so good point. So here I'm going to show simulation with k equal 3, so that's very easy because we look at the shortest guy. What we, in the proof, what we do is that we do it, then we do whatever. Here we get a tensor, you rematricize this, and you redo principal component analysis of that. We try to, a bunch of stuff. You will see curves with many curves because we tried a bunch of things. For instance, we tried to enforce the constraint. You know that once you matricize, each of these two guys is not only rank 1, but you know that it's PSD. Now, rank 1 is difficult, but PSD is nice because it's convex. So we do, power iteration for the big matrix and project on the PSD cone at each iteration. It improves a little bit, but only a little bit. Okay, so this is okay. What I'm plotting here, we are plotting here, is curves. The scalar product versus beta for different algorithm. The light one is just plain power iteration with the random initialization, and this dotted blue one is just plain unfolding, and then there is a bunch of other one. For instance, this is we do unfolding, but then we try to project on the PSD cone. We enforce that the principal component is in the PSD cone. Here we initialize power iteration with unfolding, etc., etc. Okay, so as you see, they work when beta is big enough. These work a little bit more poorly, and then we increase n to 50, and then to 100, and then to 200, and the theory, it's okay in the sense that it prescribes that all of these should have the behavior, all of these have unfolding as initialization and have roughly the same behavior. Right? There are changes here, but roughly the same behavior. This has random initialization and is quite a bit worse. And then with larger, it's quite a bit worse, and then larger, it's quite a bit worse.
Did you try ALS or something like that?
Sorry?
Did you try ALS, essentially like alternating these squares? Just make it asymmetric and just cycle through. This is similar to what...
In the matrix. In the matrix.
In the tensor.
In the tensor.
This is...
It's the asymmetric version of power method.
Yeah, this is a good question. I didn't try, but...
It's heuristic, but it seems like that's the one that...
Yeah. Good question. Okay. This is so now it's clear that they scale differently, really, the power iteration and the unfolding. And so let's see whether the theory prescribes correctly how do they scale. Okay, this is not really the theory, but because here I scale beta by square root of n, and that is the exponent. Here it's just power iteration for all the algorithm, and I scale beta by square root of n. This is the exponent that is prescribed by my heuristics. The exponent that is guaranteed by the theorem is n. And as you see, they all collapse pretty well. They collapse already at n equal 50. Okay? So despite this being kind of asymptotic, theory is decent for n equal 50. And this is for the unfolding. Now I scale beta by n to the 1/4, and they also collapse, right? So we initially thought that our proof actually was correct and gave the correct exponent 1/2. And then we tried it and didn't match, and then went back and listened. Why? Okay, so this is basically all. Here there is clearly one big open question that I think it's worth pursuing, is that, giving me a tensor of this type with beta, 0.1, is it hard or to find the principal component? I don't know how to answer question.
I mean, Boss, David, and John have this sum of squares formulation for tensor decomposition.
Well, you can. Yeah, I mean, there are ways to attack this. One is to analyze SDP hierarchies, right? Of course, and
Do we know what that gives for this problem? I mean, there's a natural semi-definite.
I don't know. I don't even have a very good guess. Yeah, but okay, another way to attack the problem is, I think this problem is actually fairly similar to planted XOR SAT, and I think one could try to do reduction from, I mean, again, you don't have unconditional hardness for that, but there are things about that I know.
What was your normalization or assumption on the diagonal? Like, by diagonal, I mean even if two entries are the same.
The truth is that it doesn't matter because there are many less entries there. The way we set it is in such a way that it's rotational invariant. So really the way we define one way to guarantee that is you take Z to be sum over all the permutation in the symmetric group of G pi modulo some normalization here, where G now is a tensor with, I at the entries, asymmetric. So it's like random matrices, right? One way to get the right normalization, you take a matrix with just completely identities, and you take that plus its transpose divided by 1 over square root of 2. So you can do the same. Now this has the nice feature that if you conjugate by rotation, it remains invariant distribution. But the reality is that as long as you don't do anything dramatic to the diagonal, it doesn't matter.
About your last remark, all the algorithms you've described here, you can think of them as statistical. You don't really need to see the entries of the matrix. And at least for planted XOR SAT, there is a similar gap. The upper bound is you need n to the k over 2 clauses.
But we see each entry multiple times, so I don't think...
You do in this, you mean? Yeah. But imagine that you didn't.
Sure.
And every time you did an iteration, you just said, okay, multiply your matrix with this, you would still get the same bounds.
Yeah.
So at least in that model, you might be able to prove exponential, n to the omega k.
Yeah, that could be interesting. But
Which holds for planted SAT.
Yeah, but again, it's not quite the same. I don't think of it as quite. It's suggestive again. It's a difficult question. So any evidence in that direction, I think it's good. But all the evidence that I see, the strongest that I see is really analyzing sum of squares. That, at least personally, I would consider if sum of squares at the same threshold as unfolding, I would give up. Okay, that's all. Thank you.